And welcome once again, ladies and gentlemen, to the Simkins Physics Corner. Last time we were together, we talked about momentum. We talked about what the impulse on an object is, that's a force over time, and how impulses change momentum. If you don't know anything I'm talking about right now, go ahead and check out the video called Impulse Momentum Physics. Today, we're going to unpack a little bit more momentum with this idea of the law of conservation of momentum. So this law, if you look it up, says the total momentum before a collision is equal to the total momentum after a collision. So first, what we're going to do is take a little field trip to space. This is a guy on the International Space Station. He is orbiting the Earth, and so in his reference frame, it looks like there is no gravity. Now, this turns out to be a great place to conduct physics experiments because we don't have to worry about things falling. They're just going to continue to move in a straight line in the way that we send them. So check out what happens in this zero gravity environment when he sends two tennis balls towards one another. Check it out. As he holds the ball in his right hand, that one right there right in front of him, it's at rest. And what is he going to do is throw the other tennis ball towards that one that's at rest. Watch what happens when they collide. Tennis ball comes in, hits that tennis ball, other one goes out fast. So you notice we had one at rest, one comes in, bonk, and then it knocks it out fast. If you've ever played a game of billiards or been a pool shark, you've probably seen some collisions like this before. Now, of course, NASA loves their Velcro. And so check out what happens when he throws the tennis balls towards one another and they stick together with Velcro, like this. Boom. We're going to take a look at these two examples and see what we can learn about the conservation of momentum when it comes to our physics. So let's take a look at it. Now, all these words can be summarized into this equation. We've seen this symbol before, this symbol called the summation symbol in your math class. Your math teacher would tell you that this symbol right here means add up everything that comes after the symbol. So add up all the momentum. P is momentum, as we learned in our last video, and I would be initial. That would be before a collision. And then this would mean add up all the momentum after a collision. And so this fancy equation, don't be intimidated by these symbols. All that's going to mean is total momentum before a collision is equal to total momentum after a collision. So what does that have to do with the tennis balls we see in space? Well, let's take a look at the three kinds of collisions that we're going to see. The first one that we saw the tennis balls do was bounce. They bounce off of each other, and so this is a fun example of a bouncing collision. If you've ever seen this bubble soccer, boom, there it is right there. Okay, you can see that the person in blue here is coming into the left, this person is coming into the right, and it looks like the person in red had a little more momentum. Why do I say that? Because the blue person got knocked over. There's another kind of collision we're going to see called sticky collisions, where you have this green block coming in pretty fast and it sticks to the yellow block and they move together. But you might notice the green block was moving pretty hot, and when it stuck to the yellow block, the system slowed down. Those two blocks slowed down and moved a little bit slower. That's called a sticky collision. And then finally, my favorite, the exploding collision. Some people, this idea of recoil when they go to the range maybe, or you're going duck hunting, they don't understand that when you send a projectile really fast that way, all right, you can't get that momentum for free. There's going to be a kickback or a recoil, and something has to move in the opposite direction. This all has to do with the conservation of momentum. So let's unpack these types of collisions and look at some of the numbers to this. Take a look at the guy in space. Over here, I've labeled this tennis ball with mass m and velocity v. And in our first example we saw, the tennis ball was not moving at all. It had a velocity of 0. And so I do a little something called the PMV stacks. You'll notice that as I set up this question, I'm going to put P, M, and V. Now, we know from our first video that P is equal to M times V, so keep that in mind as I do this math here for you today. But this strategy of PMV stacks just helps us organize what had momentum before a collision took place and what had momentum after a collision took place. So take a look at this picture. Now, this is a little on the heavy side, but let's say I just picked easy numbers for us. Let's say the tennis ball had a mass of 0.1 kilograms, and he throws it at a velocity of 2 meters per second. All right. The ball number 2 is at rest, okay, and if it's at rest, if it has no velocity, as we learned in our first video, that means it has no momentum. Something at rest has no momentum. And so let's talk about this idea of the total momentum of the system. The system is defined as the two tennis balls. Is there a guy there? Sure. Is he inside of the space station? Yeah. But that is not what we're talking about in the system. So when we say the total momentum in a system is conserved, it's a a defined number of objects or a defined space where an interaction is happening, the only thing we care about are those two tennis balls. We're not even actually accounting for his hand pushing the tennis ball initially, because we didn't say the tennis balls guy system. We just said the tennis ball system. So in the system, how much momentum do we have? 0.2 plus 0. Of course, that's going to add up to 0.2. That's why I picked easy numbers for us. Now, you might notice this is not here accidentally. At the bottom of the slide or the bottom of the screen, you see the total P before is equal to the total momentum after. All I did was break that all out into the details with the PMV stacks. Okay, so in the first part that we watched of the video, this ball pretty much came to rest after it collided, and it sent the second ball out. So the left side ball was coming in hot, the right side ball was at rest, boom, they collide, then the left side ball was pretty much at rest, and the right side ball was pretty much moving off to the right there. And so what that means then is if this ball has now gone from 2 meters per second to rest, well, where did that velocity go, or where did that momentum go? Well, actually what happens is that tennis ball transferred its momentum into the other tennis ball. Why? Because the total momentum in the system has to remain the same. And so what that means is our first ball that came to rest and the second ball that now has taken on this momentum of 0.2 kilogram meters per second, what does that mean? That means that the total momentum of the system stays the same. And that's why you see the interaction that we did. Let's go back and watch that one more time with these numbers in mind. This is around 38 seconds or so. You can see here once again, let's say this tennis ball comes in with a momentum of 0.2 kilogram meters per second. There it is coming in right there. All right, it has momentum. The other ball does not have momentum. What happens? The collision happens, and then ball number 2 takes the momentum, and ball number 1 is just kind of floating there all by its lonesome. All right, so that's an example of a bouncing collision with some numbers. Let's take a look at another one. This is the second example we saw with the Velcro. So he tosses the ball in. I'm going to call the ball to have mass m and initial velocity v. This one, remember, is at 0 velocity. It is not moving. So if we use our PMV stacks to set everything up, okay, we have the first ball moving pretty good, the second ball not moving at all, and the math's going to work out to be exactly the same. We start with 0.2 kilogram meters per second of momentum. Let's do the PMV stacks for after the collisions when they stick together. Now, what do you think is going to happen? Well, we have one thing moving, and it's moving pretty fast, and then it runs into another thing. And what actually happened? We doubled the mass. Why? Because one tennis ball was moving, and now 2 tennis balls stuck together are moving. Now, we know the total momentum has to stay the same by the law of conservation of momentum. And so what has to happen then is, because each of these tennis balls has the same mass, we've pretty much doubled the mass of the moving thing. First it was 1 ball, now it's 2. That means that the momentum is split evenly between the two, in this case only because they have the same mass, but that's because the total still has to be 0.2. And if you do the math for this, if you consider P equals mv, and you can algebra good, you have V equals P over m just by doing a little rearranging, and of course 0.1 divided by 0.1 is going to be a velocity of 1. Oops, sorry, let me go back. It's going to be a velocity of 1 meter per second. And they're each going to be moving, stuck together with a velocity of 1 meter per second. Now, this is a really cool thing. This is a very simple equation, P equals mv. Watch what happened. The speed was 2 with a mass of 1. And then the speed was 1 with a mass of 0.2. We doubled the mass, and what happened to the speed? It dropped by a factor of 2. And that's what I've written here on this diagram to illustrate. Since we doubled the mass to m, we have a resulting speed of 1/2 v, or half the initial velocity, because they've now stuck together. So that's an example of a sticky collision with the math. So you may have seen bouncing collisions. If you consider the motion of the black ball, the 8 ball, it looks like we pretty much hit it with the stick. Now, we didn't hit it with the stick. We hit the cue ball with the stick because that's the rules, and then the cue ball hit the 8 ball. But you can see how we are giving the white ball an impulse, a force times time, just to kind of bring that back into our first video. But you can see now that this white ball, the cue ball, has a lot of momentum, and then all of a sudden it stops. Well, where did that momentum go? It transferred into the 8 ball. So that's just a conceptual idea for a bouncing collision. Take a look at this from the physics classroom. This little example is going to help us understand the math a little bit better. And you can see they're kind of doing a PMV stack like I did. You see they have the P, they have the M, and they have the V. Now look at how the numbers change after these two vehicles collide and they stick together, just like our 2 tennis balls with the Velcro. You see the truck's mass obviously is not going to change. All right, the car's mass stays the same the whole time. But look at what happens before the collision. The truck's going 20 meters per second and has a momentum of 60,000. So the momentum before is all in the truck. Why? Because the car is at rest. So I didn't do the whole PMV details down here, but you can see them as they take place up in the table. Now, we know that the total momentum before a collision, sigma pi, has to be equal to the total momentum after a collision, sigma pf. And so how does that work? Well, you can see in this graphic how the truck was moving pretty fast, but when it added the mass of the car into the system, now we have the truck and the car's mass moving together. That's going to cause everybody to slow down. You see how it ends up to be 15 and 15. They're both moving at the same speed. Now, when you do the math for PMV or the PMV stacks, you see that the rule does hold true, that the conservation of momentum is held because 60,000 plus 0 is equal to 45,000 plus 15,000. So that's an example of a sticky collision, how the PMV stacks would work out for you there in a little bit of a graphical way. Let's consider an explosion, because all we've seen so far is that person getting blown backwards with the recoil of a very large rifle. Here we have two people. All right, we have the lady and the dude. Now, the lady and the dude are not moving in the initial picture. They're both at rest. So what is the total momentum of the system before? Oh, well, the lady's not moving, and the guy's not moving. So their total momentum before they push off one another is 0. Oh, well, what's the total momentum after the collision then? Before it was 0? After it has to be 0. How does that work? Well, notice I didn't say each individual person's momentum has to be 0. What we say is that the total momentum has to be 0. And this is the big idea. Who do you think has more mass? I've indicated in the PMV stacks here for you. Probably the guy. All right, he's pretty jacked, and we have a pretty petite lady over here. Well, what does that mean? That means that when the guy pushes off, even though they both experience the same force by Newton's third law, the guy has more mass, therefore he's not going to move as fast. And so if I were to draw this out, it would be like big M plus little v, or sorry, times little v over on that side, and then the lady here is bringing little m times big V. All right, do you see what I'm trying to illustrate here? In fact, we have to notice something very important here. Momentum in the beginning, the total momentum was 0. The total momentum after is still 0. So how does that work? They're both moving. How do you have nobody moving and then two people moving? Well, the answer is momentum can be negative. All right. So I'm just going to make up a number here. Let's say the guy ends up having 100 kilogram meters per second of momentum. To the right, how much would the lady have to have? She would have to have negative 100 kilogram meters per second of momentum. And the negative indicates it's to the left. All right, so that's how you can have one person go one way and the other person go the other way. When you started with 0 total momentum, how does that not violate the principle? Well, momentum can be negative, and negative 100 plus 100 is, guess what? 0. So we didn't break any rules there. Let's look at one more math here. All right, we have a noob skater girl is rolling on a board. She jumps off the board. So imagine like they're both rolling together, and then she goes, ooh, and like jumps off the board. Well, what would the board do? It might actually even kick backwards, right? And so I'm going to have to go through this example a little fast due to the limitations of my time here. But if you go ahead and look at the question, we have the mass of the girl and how fast she's moving initially. All right, so that's those two numbers right there. We have the mass of the board. And the board, of course, they're moving together, so it has the same speed as the girl. I've set that up. You can calculate P by doing P equals mv, and you would add the two momenta together. You would add the momentum of the girl plus the momentum of the board. You add those two together, the total momentum before the collision is 114. Well, that means the total momentum after the collision has to be 114. And so if we take the girl with her new speed, she jumped forward off of the board, so she started moving faster forward. Well, you can't do that for free. Something has to recoil and go backwards in response. And so if we use P equals mv, we find her momentum here, 137.5, and you're like, wait a minute, how can the total add up to 114 if she has 137.5? Well, that's a good question. 114 equals 137.5 plus what? Oh, a negative. Oh, because momentum can be negative. If the board goes backwards, that means it has momentum in the opposite direction. And then we know the mass of the board, and by P equals mv, we can solve for the velocity. It looks like that board is going to be moving pretty fast backwards. So in the first video, I promised you guys that I would explain why this guy gets it so bad. And by this guy, I mean the guy with the white medicine ball on the left side. Well, now that we know a little bit more about momentum, look at what's happening here. You have three other guys, two with blue medicine balls and one with a purple. You notice that each of these guys is bringing a little bit of momentum to that side of the screen. Sorry, Yeah, that side of the screen. Sorry, it's flipped for me. They're all bringing that, and the guy with the white ball is not bringing too much momentum. So what's the result? Well, the guy with the white ball, after all these guys come to rest, that momentum has to go somewhere. Where does it go? It goes all into the guy with the white ball. So whether you're watching a football game and you see somebody tackle another player, whether you're going duck hunting and you didn't take a very good stance and you fall over backwards, or whether you're trying to outrun a giant hamster wheel down a hill, because that happens all the time, keep these ideas of the conservation of momentum in mind. The total momentum before a system has to equal the total momentum after a collision in a closed system. Hey, if you like this video, go ahead and check out the Simkins Physics Corner. We got hot physics content dropping for you every day. Be sure to hit the like and subscribe button so you guys can get all of the new videos that are coming out, and hit the bell. Ring a ring a ring a. This is Mr. Simkins in the Simkins Physics Corner. I'm out.